Speaking of reliability, a podcast with good friends talking with you about reliability engineering topics. Welcome to Speaking of Reliability. This is Fred Schenkelberg.
And this is Chris Jackson. We're going to be talking about what happens when wind turbines fail, at least for a very specific application.
That's right. So we got a question through, I think it was through email. And it was, they have 90 wind turbines and started operating in 2022. And so far, I'm quoting here, so far, 3 main bearings have failed. And I imagine those are pretty big bearings and probably not a quick swap out. So after root cause analysis and discussion with the manufacturer, it's been established a serial defect, which I'm interpreting as this is going to happen to all of them and it's going to fail much sooner than they should. And because then they went on to do a Weibull analysis, 3 failures and 87 suspensions, in trying to forecast when that whole population is going to have failed out, and which I think is kind of risky in and of itself. But you didn't ask about that analysis, so they want to do proactive replacements to prevent catastrophic failures, which I think is a good thing to think about and do. Here comes my questions. How do I treat these proactive replacements knowing they are going to fail anyway, eventually? I think he partially answered his own question there. And should I consider these proactive replacements as failures or suspensions?
Well, this is going to be a very short podcast.
Well, that was the first question. There's a follow-up there. But they haven't failed yet. So there's suspension. In my mind, I don't know. Does that make it a short one because you agree with that? Or is it?
Yeah, I would agree.
Okay. Yeah. So I wrote back to him with that, and he says, well, that's not going to help. The next question was, all right, we have 87 out there we're going to proactively replace. Which ones should we replace?
So just to clarify, the Weibull analysis they did on the 3 that failed, was that the only piece of information they used to conclude that everyone else was going to fail as well?
No, they did a root cause analysis and found it was, he calls it a serial problem. I think a systemic problem in the batch of products.
Or endemic, or every wind turbine has it.
Yeah. In that particular batch they had, we didn't get into it in the discussion with this person through the email, but a common practice is this a one-off, or is it the whole batch, or is it the whole design process itself? What's the scope of the problem? And they came to the conclusion that it was, all 90 have this problem and will fail sooner than later. And then they said, given the nature of it, if that main bearing fails, imagine that leads to those really unpopular flaming towers with windmills melting off, blades melting and falling to the ground in flames. It's probably what they're trying to avoid, is making that newsreel by going out and actively replacing these things. So I get that. It's a problem when the main bearing fails.
Well, the other thing too is proactive replacement allows you to control when things need to be offline. You can't control when it fails. So even if it's not like turbine blades flying Michael Bay movie style at Mark 17, it's still very prudent to be able to do that, to control when each wind turbine comes offline.
Yeah, and you can minimize the amount of downtime. All kinds of good things happen when you're proactive like that on it. So then the follow-on question was, when do we, is there a way to tell which order we should replace them? And I thought, well, bearings tend to show, and we didn't get into the details of what was wrong with the bearings, but if it creates vibration, maybe there's a signature that you can detect without taking the damn thing apart, that, this one's about to go, we need to move it up in the schedule versus not. That might be one way to do it. And I know there's other folks in the world that have a lot more experience of monitoring wind turbines. But I'd start looking at the non-destructive measurement systems to say, and it's really contingent on what is the nature of the failure mechanism.
Yeah. The other thing too, though, is this: if you do have play, like if they're not going to fail soon, then the order would be an operational one. So if you can limit, let's just say you can sort of be relatively confident failure won't occur. The risk of failure is not too high for the next 6 months for 10 of them.
Right.
Well, you might choose the one which is the most operationally prudent to replace today, because that wind turbine powers, I don't know, something that's seasonal, like a touristy place where there's seasonal tourist influx is low. That sort of
Oh, okay. So
conversation.
it's kind of a combination of which one we would like to keep running because of it's in demand right now, or
Yeah,
we
definitely.
generate revenue because this one's operating versus other times a year where we can't sell it as much. Or if they're all in one field, then it would be whichever one's easier to get to. Go to the closest one first. It could be a bunch of factors like that to deal with it. The but there are vibration analysis, oil analysis, depending on the system setup. It could be electrical signatures that you're getting that say this one's further along than another one if it's a wear type mechanism, which is not terribly uncommon with bearings, but I don't know the details of that. But that'd be one way to look at it. The other thought was, how can I improve my prediction? If we're going to suspend all the ones that we proactively replace, is there something I can do to improve the analysis? Because we only have 3 failures.
Mm-hmm.
And I thought, this is a question for Chris. Because, and I'm completely forgetting the name of it, but in Reliasoft, and there's a handful of other packages that do this, is that you can, it's more of a maintenance thing. Is this equipment, because old style, we would assume it was say you replace that main bearing and now your system is good as new, which assumes everything in the system is good as new. Well, for this particular case, the bearings are 2 years old, 3 years old. The rest of the system is 2 or 3 years old, and maybe that's close enough to good as new. I don't know. That's a judgment call. And there's the other assumption is they're as bad as old, right? The new bearings are just 3 years old now. We just kind of paint them as being worse than they really are. But it was something I saw where you can do the system by component level, can say, oh, the bearings are new, but everything else is old. So it's like 80% or 60% or whatever, some percentage or ratio of good as new. It's not 100% and it's not 0% good as new. It's some ratio in the middle. And it was a way to do the analysis for repairable systems to take into account the variability of when particular key components were replaced. Gave me the thought, maybe we could do that. If you can take apart these bearings and see, assuming it's a wear type system, how far along in that wear process is it? Do we have information that says, yeah, this one's going to fail in a week and this one's going to fail in 6 years due to the amount of damage done, for example? And then use that back into a Weibull analysis to partially censor stuff. And I have never heard of a way to do that in a Weibull analysis.
Yeah. So I've done this for vehicles where I looked at the post-servicing failure rate. When I say I've done it, sort of done it in terms of mimicking what you're talking about. But the thing you're talking about is a general renewal theory, which a lot of PhDs have been done on it, which is fantastic. But also, where you have good as new, good as old, and anything in between. And there's a lot of statistical sophisticacy behind it. And I made that word up, I believe. Sophisticacy. I'm going to run with it.
Yeah. Fancy math.
Yeah. But the problem is that I think it's furiously solving the wrong problem. We do know that every time you touch something, you increase the likelihood of failure for a short period of time at the very least, because every time you touch something, it's an opportunity for error. to be introduced. And even if it's, one time out of every 10, you will see an appreciable increase in the failure rate after servicing or maintenance or overhaul or replacement, no matter what you do.
Yeah. No, I'm laughing because my favorite story is I was working with a team they would lay these fiber optic systems and detectors over a large area. And then they had a great big machine that was called a thumper. And it would just send these low frequency waves out through the ground, and these sensors would pick it up. And the reflections from the structures under the ground was used for mapping where oil might be and stuff like that.
Mm.
And they showed me one of their connectors for these fiber optic cables, and it was a repeater, I think it was with the device it was. And it had "do not kill snakes" with this stamped great big paint on all four sides of this rectangular cylinder, this device. And like, seriously, people use this to kill snakes? Yeah, you jump out of a truck in the desert, there's a big snake there, and you're holding this thing that looks like a club. Yeah, they use it. It's like, so I digress. Mm-hmm. But the idea of the general renewal process, I think, is for repairable systems. And you got, and the overall wind turbine is a repairable system. It's not, you don't want to repair it. It's not a trivial thing, but it can be. And yeah, there's some cool stuff in it. But you mentioned that it was solving the wrong problem.
Because the assumption is that it's as good as new or as good as old or anywhere in between. But we just talked about how it's going to be worse than old temporarily and go back to, something hopefully better than old.
Well, we hope we didn't add another failure mechanism. One of the, you broke a cable off, or you bent a lever, or the valve wasn't shut completely, or whatever. You stepped on the wrong place, or happened to jump out of a truck and smash a snake with it, just so you could continue with the process. Yeah, anytime you touch something, it makes it worse.
Yeah, but the other thing about wind turbines, and I don't want to pretend they're not complex, but they're not complex, as in they're
not a battleship.
No, they have, like, the bearings in a wind turbine. They're no joke. They are machined, designed with incredible care and precision, as a rule. So I'm not trying to denigrate it, but you still only have one of those. And that makes data analysis so much better. And so when it comes to modeling the reliability of wind turbines, there's no reason why you can't model the reliability of wind turbines. Like you said, the battleship, that's much harder to create a fault tree for than a wind turbine. So there's no reason why you can't create a fault tree or an RBD for a wind turbine where the bearing or whatever it is you're replacing is just one component, and get a good understanding of everything else, and then update your system reliability model thereafter. I've seen people pursue general renewal theory over just taking the time to model these systems time and time again. And that's what I meant by furiously solving the wrong problem.
Well, it's what I think the central question, the way I responded to him was, because he was dealing with that we're proactively replacing those. So if they do get some failures, then they'll have more data points for his viable model for the bearings themselves, right? And get a sense of, do we have 6 months, or has it gotten worse? Do we have 3 months, or whatever their timeframes they're talking about? But they had to get failures to have meaningful data. And the longer it runs without failure, and if they're using maximum likelihood, it takes into account that duration as the sensor data. So that's a little better on your estimates, but you really like failures, but you're trying to actively to not get failures. So I had the thought, well, how about if you know the relationship between, and I'm making the assumption that it creates damage before it fails. It's a wear out mechanism, or a wear, or some mechanism they can monitor the damage and relate that to its expected time to failure, like a degradation model for that bearing failure mechanism, and translate that into a time to failure. Even though it didn't actually fail, if they know it was 90% there on some relationship, they could say, oh, it's only got 3 minutes and 16 seconds left, or maybe something more precise if that's needed. But the idea is that they could use, it really is contingent on the type of failure mechanism. And if they want to spend the money to do the failure analysis and happen to either have or create a relationship between that kind of damage and its time to failure damage model, they may be able to extend out through degradation modeling when it would fail, and then use that back into their overall 90 system model to get a little bit more information than it just didn't fail yet.
The only problem with that, because I agree with what you're saying in principle, and we need to know more about the issue at hand. But when he says it's a serial problem, I'm guessing that it's a defect, which can be infuriatingly difficult to model when it comes to degradation.
Yeah. If it's in the bulk material and it's crystalline growth or something, that it would have to be a well understood pattern to failure, damage pattern to failure, like a crack propagation kind of thing.
Yeah, but even then, when you have that, we have a pretty good understanding of crack propagation models. But I found this in the past, that when I modeled diodes, laser emitting diodes, high power laser emitting diodes for a LiDAR application, we were able to find that there was a very unique signature for infant mortality. And a lot of people look at infant mortality as sort of the decreasing slope at the front end of the bathtub curve, and they're not wrong for doing it that way. It's just that in the Weibull plot, essentially what happened was we didn't see sort of the bathtub curve. We saw two line segments. So one line segment for the first 3.3% of diodes with a particular slope, and then exactly the same slope just to the right for the remaining 96.7%. And so what we surmised was that there was a very specific defect being introduced when they're creating the silicon crystal for these laser emitting diodes. And again, creating laser emitting diodes, silicon crystals, it is no joke. That is extraordinarily challenging. And by definition, you tend to have imperfections. It's all about how you control those imperfections. But it looked like about 3% had a very specific defect, which was essentially accelerating failure in exactly the same way. When you have that sort of gradual decrease in the bathtub curve, what that means is you have lots of defects or issues causing problems, but they're all over the place. They're not the same. They're all accelerating in their own unique way. And which brings me back to my first point, is it can be very challenging to understand the degradation time to failure model when you have a problem that exists, but you can't be certain that each bearing has exactly the same defect in terms of its effect on time to failure.
Yeah, if the first three failed and they did failure analysis on it, root cause analysis, the next three may not necessarily be the same defect or issue or problem. They seem to believe it's a batch problem affects all 90, or some issue that affects all of them. So they answer it more better, as my English teacher would roll her eyes, but is, that's where diving into the root cause analysis and the details and understand the material science or whatever aspects of this mechanism are, there are some areas you might be able to do better at it. And in the meantime, get busy replacing them. that's about, and maybe you can use some non-destructive monitoring of some sort to detect which ones are further along or not, again, dependent on the nature of the mechanism. So it's really hard to know without way more information. But you got to be, I think the gist of it is that when I answer this question, it's like, I appreciate the question, and I appreciate asking the questions of how to, do I censor these or not? And what else can I do? He's already thinking. He's like, how can I help this organization solve this problem in a meaningful way and minimize risk and all that other good stuff? That's what we do. And so I think that was appropriate. But Yeah, just a couple of thoughts I threw out there. Too many assumptions because we don't know enough of the details, but that's okay. It sounds like they got a good person working on it, so hopefully
Yeah,
they.
they're asking lots of really good questions, and they're not asking how do I do nothing.
Yeah, yeah. How can I ignore this until my next paycheck? And kind of thing. Now, so I mean, if you've got a question, if you're listening to this and you're faced with, so what are the options to approach some issue or problem or a statistic or whatever it is you're facing? Those are the things we kind of live for. Well, maybe not, but we enjoy them. I should put it that way. We'll try to get an answer back to you, or we'll get you in touch with somebody that probably does know a better answer. And we'll probably chat about it on the show so others can learn from your question and encourage more questions. So there's lots of ways it helps us and our whole community. So if you're got an idea or a question or a comment on one of these things or something you're working on, shoot us a message. You can go over to accendoreliability.com/go/SOR. A couple of ways to get in touch. And you can get a hold of Chris or I or the other hosts of the show through LinkedIn or our About pages. And so just another case of a bad bearing, Chris. Just another case. So thanks so much, Chris. We'll chat with you soon, and hopefully we get another question to dive into.
Yeah, it's a good one.
Thanks for listening to Speaking of Reliability. We invite you to join the conversation. If you have a question or a topic that you think we should discuss in a future show, please let us know. You can find a comment box below the episode show notes, or just leave a note as part of a review on iTunes.